In this video, we're going to discuss the common ion effect. What the common ion effect stipulates is that if one of the ions that would go into solution when your solid dissolves is already in solution from another source, well, that affects the equilibrium concentrations and can change how much of your compound can dissolve. So first, what if we just put lead iodide in 1 liter of water? Normally we'd set up that our KSP is going to be equal to the lead 2 plus to the first power and the I minus to the second power, because our lead iodide solid will be in equilibrium with the ions lead 2 plus aqueous and 2 I minus aqueous. We're going to find some equilibrium concentration. That'll be X for the lead, and that'll be 2X for the iodide, because we'll have twice as many. However many lead iodides fall apart, I'll get that many leads, and I'll get twice that many iodides, which is going to give us, as we distribute that 2, it's going to give us 4X squared times X for 4X cubed. Must equal our KSP of 7.9 times 10 to the minus 9. Divide by 4. 1.975 times 10 to the minus 9 must equal x cubed. Take the third root. X is equal to 0.001255. So we can find that if you try to dissolve lead iodide in water, you'll only get 1.2 millimolar lead iodide to dissolve. Generally, we think of lead iodide as insoluble because that's a pretty small amount. If you take a solution of lead nitrate and sodium iodide and you pour them together, you instantly get this yellow powder forming in solution. Because as soon as lead and iodide pair up, the vast majority of it cannot stay solubilized. So we have our lead iodide solid in equilibrium with that lead 2 plus aqueous and those 2 I minus aqueous. And they're sitting around at the start just being 0.001255 molar, so in 1 liter, and twice that, 0.00251 moles. And as long as this is their concentrations, they'll be at equilibrium. Well, at equilibrium, we always have to equal the equilibrium constant. So KSP, 7.9 times 10 minus 9, is going to be equal to 0.001255 to the first times 0.00251 to the second. Well, let's just imagine for a moment that we're going to solve some Q values. Let's increase one of these. So if I had the same lead concentration, 0.01255, but I raised my I minus to 0.0251. Let's just move it up 1 decimal. So we shift that decimal over 1. It is 10 times more. Well, if I was to calculate this out right now, what we'll find is our Q is 7.9 times 10 to the minus 7. Why is that? Well, I put in 10 times more things, and it's squared, so it comes out 100 times bigger. When I do this multiplication, it just looks 100 times bigger. And you'll see that in our exponent. It got 100 times bigger, 2 orders of magnitude change. Well, Q is presently greater than KEQ. And if your Q is greater than KEQ, you have too much product, too little reactant. And so you're going to start losing product. You're going to favor going back to starting materials to reach equilibrium again. This makes sense. I suddenly added a whole lot more of one ion when I was at equilibrium, so now I'm above the equilibrium amounts. It'll have to change to go back. Well, how much will it have to change by? Well, let's just imagine that I had my KSP was equal to some concentration of lead and our known concentration that we just set of 0.0251 of my I minus. I can actually solve out what that lead needs to be for me to be at equilibrium. Forget about changing in things, just what would lead need to be if this was my concentration of iodide? I can move my iodide over here, divide by it, and solve for my lead concentration. Must be 1.254 times 10 to the minus 5. Well, originally it was 1.25, well, 5, slight rounding error there, times 10 to the minus 3. So we've moved 2 orders of magnitude. Well, this makes sense. That's what I ended up doing before the other direction. My iodide went up by effectively 100 times. So my lead had to go down by 100 times so that when I multiply together, I get the original KSP. So if we increase the iodide concentration 10 times more, we end up with 1/100th as much lead. Now this works because it's got the square in there. If we'd had a 1-to-1 ratio, it would be 10 up and 10 down. But the idea is as we adjust the equilibrium, by raising one component, we will fix that equilibrium by dropping the other component. So what happens if I take this original mixture and we raise I minus to 0.1 molar? Let's just crank it up even more. Sodium iodide is cheap. I can get a bunch of iodide, I can pour it into my container, and it'll flood over, and so my iodide is 0.1 molar. Molar solid. We're not concerned, its concentration doesn't change, but this means what does our lead need to be if we've raised our iodide this high? And so our KSP is going to equal our lead, which will be some unknown yet, and our iodide, 0.1 squared. Now we said our iodide is 0.1, so we're not multiplying it by 2 or anything. That's when we're disproportionating and we're saying, hey, I'm making both of these products and this one I make twice as much. In this case, we just physically set how much iodide was in our solution. It's still squared though, because the coefficient still needs to show up in the expression. And so 7.9 times 10 minus 9 is going to equal x times 0.1 squared. Rearrange and solve for x. We'll find it is 7.9 times 10 to the minus 11. When we had just lead iodide in pure water, our actual free lead concentration was equal to 0.001255, or 1.255 times 10 to the minus 3 molar. By putting in some iodide, a cheap and reasonably obtainable ion, into this solution in addition, it forces that equilibrium to shift that our lead is now 7.9 times 10 to the minus 11 molar, 8 orders of magnitude less. Having the common ion iodide in solution from a second source forced this equilibrium to dramatically reduce the amount of lead that could be dissolved in order to maintain its equilibrium. So significantly that you can effectively remove almost all contaminant metal this way. 10 to the minus 11 molar is well below any safety level for lead. This is incredibly tiny amount of lead. But lead iodide on its own, 1.2 millimolar, is actually quite a bit of lead. And so in water treatment systems, it is not uncommon to add certain ions in order to push out contaminants from the water. Remediation of mine wastewater and the like can do this. We also do this a little bit for radioactive elements. There's quite a bit of work done on how to isolate radioactive elements that get into water supplies after an accident or a breach at a reactor and the like. Being able to crash those out as solids and reduce the radioactivity of the water so that it doesn't provide as much contamination downstream is a very significant health aspect. And so the ability to force one ion to be far less soluble by adding the other ion from the mixture is a useful way for purging out some things from the solution.